Hello and welcome back. So this is the introduction to the normal distribution, and the normal distribution is a continuous probability distribution, and it is the only continuous probability distribution that will be specifically studied in 2020 due to the changed study design. So the normal distribution is one of the most widely used continuous distributions. You've probably heard about it before. You would have talked about normalizing data in further maths if you study further maths, and it's characterized by a bell-shaped curve that probably is familiar to most people. We represent its mean with the symbol, the Greek letter mu that you can see there, and the standard deviation with the Greek letter sigma. So the mean, you might remember from previous years, we get by adding all numbers together and dividing by how many pieces of data we have. The standard deviation is a measure of spread. It's essentially the average distance that any point is from the mean. So this is what our normal distribution would look like with the typical bell-shaped curve. We always have here at the center, we have the Greek letter mu. The normal distribution is always symmetrical, so we would end up with 50% of possible data points on one side of the mean and 50% on the other side. And as mentioned, the standard deviation sigma represents the average distance of any point from the mean. So some specific properties. Theoretically, the curve can extend indefinitely, so x can take all values. So when we saw our bell-shaped curve like this, technically, that one doesn't look quite symmetrically, but anyway, technically both ends continue indefinitely to negative and positive infinity. The curve never actually touches the x-axis. We say theoretically because in some practical situations it won't actually make sense to consider it in that same way. I mentioned before the curve is symmetric about the mean. So remember, this Greek letter mu represents the mean, and the curve is symmetric about the mean. So when I was to draw this, for it to be symmetric, that means at this middle point here we get not just the mean, but the mean, the median, which remember is the middle number, and the mode, the most commonly occurring number, all occur at that center point. One of the properties of a continuous probability distribution that you might recall is that the total area under the curve equals 1. So because this is a property for all continuous distributions, it's going to be the same in this case as well, that the area under the curve is equal to 1. There is a specific formula for the equation of the curve, which is given by this formula here. Now obviously that doesn't look like a whole lot of fun. For 2020 with the revised study design, this formula is on the formula sheet for the revised study design in 2020. So if we're looking at it carefully, we can see that it's an exponential function, which is why we would assume there would be an asymptote along here, which is why my graph will never touch the x-axis. It looks a bit different to most exponential functions, and that's going to be to do with the squared symbol here. You can also see that this curve is determined by the standard deviation and the mean. So depending on the standard deviation and the mean, that will give us a slightly different shape. If we wanted to find the area under the curve between 2 points, so here if I was finding the probability from A to B, that means I would integrate the area under the curve between A and B. So for our continuous probability distributions, the probability is given by an area under the curve. So if I was finding the probability from A to B of this area under the curve, then I would anti-differentiate this function between my value A and B. So that's similar to our integration work that we've done before. All right, if we think about what the effect of the mean and the standard deviation will have, the mean we know locates the center peak of the distribution. So here we can see as the mean changes, all of these would be different values of the mean, mean 1, mean 2. As we change the mean, we change where the center peak is located, or we can think about it as translating left and right. The standard deviation determines the width of the curve. So here they all have the mean at one point, that's all the same, but what is changing is the standard deviation, which is changing the width of the curve. So if we just take a moment to have a look at a particular example of how these might change. If I was to change the mean, we can see by changing the mean, I'm shifting my curve one way or another. Mean of 6.7 means that it is centered around the point where x is 6.7. As we change the standard deviation, what you might notice is that as the standard deviation increases, the curve becomes more spread out, but it also becomes flatter. And the reason for that is that the area under this curve needs to be consistently equal to 1. If the standard deviation is smaller, we get a very narrow curve. It's very high because it has a small standard deviation, so the data is not well spread out, but it is very narrow and very tall so that we still have an area under the curve of 1. So as we change this, the area under the curve is always 1. If the standard deviation is larger, the curve will appear flatter. Let's head back to the slideshow. So we can also talk about the standard normal curve. If we ever hear written standard normal, and this is quite common language used, the standard normal curve has a standard deviation of 1 and a mean of 0. So we are going to come back to this again later, but these 2 points, standard deviation of 1 and mean of 0, is how we define the standard normal curve. So therefore, if we were to substitute those values into our formula, we get a more simplified looking curve for the standard normal distribution. And that means that if I was to sketch it, it's going to be centered at 0, where the mean is, mean of 0, and a standard deviation of 1, representing how spread out it will be. So let's look at how we can use this function to solve some problems. Here we have a probability density function for a normally distributed function. So we're looking at this here, which is our normal distribution. And if we were comparing this to our formula on the formula sheet that you probably recall and have written down from just before, which was 1 over standard deviation of 2 pi e to the power of -1/2 x minus the mean over the standard deviation squared. Now if we're comparing this, we can see that we have a value of 3 here and here, which means we would get a standard deviation of 3, and this value here correlates to 4, we would get a mean of 4. However, there are other ways to work this out that's based on calculating mean and standard deviation for a continuous distribution. Now this is something that will probably not be explicitly assessed in 2020 due to the change of the study design, but it is still worth knowing just in case and having in your bound reference. When we're asked to find E of x, or the expected value of x, is another way of asking for the mean. And the way we work out the mean for a continuous variable is that we integrate from the smallest value to the biggest value of x multiplied by the function dx. So if we were working this out in this case, I would be integrating from negative infinity to infinity. If I multiply this function by x, we would get x over 3 square root of 2 pi, exponential our function here, x minus 4 on 3 all squared dx. And now we would use our calculator to evaluate this. So if we were looking at our CAS, we can type it in, as you can see here, typing x's as our variables, using all of our powers. We want to evaluate this and see what value we get. And this tells us an answer of 4, which means it's another way of telling us that our mean is 4. In this case, we could have read it straight from the formula, but this is a way of clarifying, consolidating, confirming that the mean is 4. Now, when we go from negative infinity to infinity, sometimes calculators might not like that very much. So just in case, if you ever have the issue where it's spinning and spinning and it's just not working for you, the calculator memory isn't working, what you can do is take the formula, use interactive calculation integral, and instead of integrating a definite integral, we can integrate a numeric interval. So when it's doing it numerically, it's essentially working out the area under the curve by using lots and lots of really small rectangles. So it will only ever give you a decimal answer, it will never give you exact values, but it is a way for it to integrate things when your calculator's not being helpful. So I would say my lower limit, my lower terminal is negative infinity, my upper terminal is infinity. The tolerance is to do with how accurate we want to be, and click OK, and it will evaluate for you this way as well. So that means here that our E of x, or our mean, is equal to 4, which we did already know, but we're clarifying it. Now we want to find E of x squared. So when we're doing E of x squared, that just means that I'm this time putting x squared multiplied by my function. So x squared multiplied by the function dx. So I'm going to get a very similar integral to what I just had, from negative infinity to infinity, but this time I'm going to be getting x squared over 3 square root of 2 pi, e to the power of negative a half, my same function before. The only difference is that I have an x squared out the front. And we will put this into CAS. So we're taking the same one, but instead of x, we want it to be x squared, and we will evaluate this. And we get an answer of 25. Now, with an answer of 25, what we can also say with this, and this is another formula that is not explicitly mentioned in 2020, but is still worth having in your bound reference. To work out the variance of x, what we do is that we take e of x squared that we just had, e of x squared minus the mean squared. So this is another useful one to have in your bound reference in case it does come up this year. So when we're working out this, let me just try and choose a colour. No, there we go. Okay, so what we're doing here is we're saying variance of x is equal to e of x squared, which is our value we got here, 25, minus the mean squared. This is our mean, that's our mean, minus the mean squared. 25 minus 16 is going to give us 9, and the standard deviation is always equal to the square root of the variance. Variance is really just used as a step towards standard deviation. And we get a standard deviation of 3, which again we did already know, but this is our way of confirming that we have a mean of 4 and a standard deviation of 3. Now if we want to describe the transformations that must be applied to the standard normal curve to get to this one. So let's recall what the standard normal curve looked like. The standard normal curve had a standard deviation of 1, so it will look just like this. And it's going to have a mean of 0 and a standard deviation of 1. So that was our standard normal curve. If we are comparing the two to determine our transformations, our differences are we have this 3 out the front, 1 over 3. This 1 over 3 can be taken over here. It affects the y. So because it affects the y, that means we can say it's been dilated by 3 from the x-axis. So dilated by 3 from the x-axis means that it's wider than the standard normal curve. We've also got this 3 here, which is inside our function there. So this one inside means that it's been dilated by 1 over 3 from the y-axis. So as it's got wider by 3, it's also got shorter by 3. And the last one, we've got this 4 here, which means it's been translated by positive 4 in the x direction. So what we have is the first two are referring to the standard deviation. It's got wider but shorter, which is why we still have an area under the curve of 1. And the second one is referring to the mean. Now just before we end for today, I also wanted to show you how we can use that formula to calculate a probability. If I wanted to, for this function, work out the probability that any value of x was greater than 5. How we do that is we set up our integral. Our smallest value is 5, our biggest is infinity. Our function goes inside and we're going to integrate with this with respect to dx. What this would be looking like, we have our function. It has a it has a mean of 4, and we're wanting to find the probability from 5 to infinity, so that means I'd be looking at this part here. So when we put that into the graph, hopefully you can already see that it is going to be a number that's going to be less than 0.5 because it's less than half of the curve I've shaded in. We don't need x here anymore, we're just using our whole function. We're going from 5 to infinity. And we put that in and get an answer. So this means that our probability that any value is going to be bigger than 5 in this case is equal to, where's it gone again, 0.3694. So 0.3694. And that's how we can use the specific function to determine normal probabilities and to find the mean and the standard deviation. So that's all for today. Remember, as always, if there is anything that you're unsure about, please make sure that you ask me, and I will see you next time.